Okay, let's dive right into this explainer and completely transform your raw foundational knowledge of Cambridge computer science into absolute gold standard evaluation. Today, we're zeroing in on one of the most notoriously tricky, yet absolutely vital areas of the entire syllabus. I'm talking about producing normalized database designs. Now, we are specifically targeting the high-level analytical skills required for syllabus code 9618, but listen, the core computational thinking principles we're about to unpack here are universally applicable. Whether you're studying 0417, 0478, 0983, 0984, or 2210, you need this. Normalization isn't just some boring rote memorization exercise, it's the ultimate test of your logical structuring and your data architecture skills. It's like a giant puzzle, and if you can master this puzzle, you literally hold the keys to unlocking top-tier marks across your entire exam paper. So grab your notebooks, get hyper-focused, and let's turn that base-level understanding into absolute exam gold. Now, I want you to consider the sheer, undeniable reality of the high stakes involved here. This is not a topic you can afford to just skim over and pray it doesn't show up. No way. A senior Cambridge examiner has explicitly confirmed that producing normalized database designs appears in every single examination series. Let that sink in for a second. Every single one. It is a fundamental, guaranteed component of your assessment. The examiners know that if you can systematically normalize a complex, messy, real-world data set all the way into third normal form, identifying those pesky partial and transitive dependencies along the way, you possess the advanced analytical depth they are desperately looking for. Because this topic is an absolute constant, mastering it doesn't just give you a chance at a few extra marks, it builds a reliable, unshakable foundation for your final overall grade. So to get you to that ultimate level of mastery, here is our exact playbook for today. First, we'll tackle the normalization challenge. Second, the core theoretical principles. Third, the method mark strategy. And finally, the top examiner traps you absolutely must avoid. Let's kick things off with Section 1, the normalization challenge, and exactly why so many students end up dropping crucial marks here. Look, we all know the textbook theory, right? Moving from first normal form to third normal form, removing repeating groups, eliminating partial dependencies, eradicating non-key dependencies. On paper, it sounds pretty straightforward, but why do students find applying these database concepts to unfamiliar contexts so incredibly hard? I mean, you might be perfectly capable of normalizing a basic student class teacher database because, well, you've seen it 100 times in class. But what happens when Cambridge suddenly throws a completely alien scenario at you? Say, a relational database for a deep-sea submersible maintenance schedule, or maybe a massive global supply chain logistics system. The underlying data rules haven't changed one bit, but that unfamiliar context acts like a total smokescreen. It causes panic. To truly answer why this throws candidates off their game, we need to look at how two very different types of students typically approach these high-pressure exam questions. Let's look at the two most common pitfalls we see time and time again in past paper responses. On the left, we have Alex. Now, Alex has memorized every single definition in the textbook. Every single one. But when faced with an unfamiliar database scenario, Alex totally panics and just brain dumps raw facts. Alex will write huge paragraphs explaining what an atomic value is or what referential integrity means, but completely fails to analyze the actual data provided in the question. Alex writes a ton, but scores almost nothing because there is zero contextual analysis. Then on the right, we have Sam. Sam is a fast thinker, really smart, but rushes the execution. Sam completely ignores the specific command words required by the syllabus. If the command word is evaluate, Sam might just describe the normalization process, totally missing the requirement to actually discuss the trade-offs of the design. Both Alex and Sam are working hard, but they're leaving massive amounts of marks on the table. Which brings us perfectly into Section 2, the core theoretical principles. Let's fix these mistakes by understanding what the examiners actually want from you. But before we continue, subscribe to our YouTube channel Ace the Exams, at acetheexams_IGCSES, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so the absolutely crucial point here is that examiners are not looking for a shallow list of terms. They don't just want vocabulary. They're looking for logical, structured, evidence-based reasoning that integrates seamlessly with other syllabus areas.
Think of normalization as a puzzle of pure logic. Superficial breadth, like just knowing the names of the normal forms, is no longer enough at this level. You need analytical depth. You need to be able to look at an unnormalized table, instantly spot the update, deletion, or insertion anomalies that would occur, and logically reason your way through the decomposition of those tables while maintaining strict data integrity. It's all about proving why a specific attribute must be moved to a new table and linked via a foreign key, rather than just stating that it happens. You have to show them the why.
Your answers must explicitly hit these three distinct cognitive domains, moving way beyond basic knowledge into actual application and deep analysis. Cambridge structures their exams entirely around these assessment objectives. Knowledge and understanding is simply knowing what a primary key or a transitive dependency is. But listen, that is just the baseline. That gets you in the door. To get the high marks, you must demonstrate application. That means taking that textbook knowledge and applying it directly to the specific, unfamiliar scenario the exam paper has given you, like that deep-sea submersible database we talked about. And finally, you must show analysis. This means breaking down the complex information, identifying the relationships between different data entities, drawing intelligent conclusions about the efficiency of the proposed database design, and actually understanding how data structure directly impacts system performance.
So how do you actually achieve that analytical depth? Top-scoring candidates decode the command words and structure their responses using the PEAL framework. This ensures every single point you make links right back to the specific exam scenario. PEL stands for point, evidence, explanation, and link. Let's walk through it. First, you make your point. For example, the database is currently not in second normal form. Boom, clear and direct. Next, you provide evidence directly from the exam paper. You write, because the attribute supplier name depends only on supplier ID, which is just one part of the composite primary key. You're pulling from the text. Then, your explanation details the technical reasoning. This is a partial dependency which can lead to data redundancy and update anomalies if a supplier's name changes. Finally, and this is the most important part, the link connects it all back to the specific scenario. Therefore, extracting supplier ID and supplier name into a separate supplier table ensures that any updates to supplier details in the logistics system only need to happen in one place, maintaining data integrity. If you structure your answers exactly like this, you become mathematically impossible to penalize.
Let's move to Section 3, the Method Mark Strategy. This is where you learn to show your work and harvest those free points.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, back to the strategy. Examiners literally award you points just for showing your process, even if your final tables end up being flawed. By executing this 5-step standardized sequence, you guarantee you are picking up method marks even if your final database schema calculation is slightly off. Step 1, identify key elements. Get your pen out and literally underline the primary keys, potential foreign keys, and repeating groups directly on the exam paper. Step 2, apply principles. State clearly on the page that you are now moving to 1NF by removing repeating groups. Tell them what you're doing. Step 3, execute with working. Physically write out your intermediate tables. Please do not try to jump from unnormalized straight to 3NF in your head. It's a trap. Write down the 1NF tables, then the 2NF tables. Step 4, verify results. Take a breath and quickly check. Does every non-key attribute depend on the whole key and nothing but the key? Finally, step 5, present format. Clearly draw out your final relational schema using standard notation, like underlining primary keys and italicizing foreign keys. Examiners love, and I mean love, to see this clear tracked progression. It visually proves your computational thinking. For more complex algorithmic thinking and those really broad database design questions, you want to apply this 3-step problem-solving loop to break down the given information and make completely justified recommendations. First, deconstruct the given scenario to deeply understand the business rules. Ask yourself, can a customer have multiple orders? Can an order have multiple products? This immediately dictates your entity relationship modeling. Second, solve systematically by applying your normalization rules step by step, just like we discussed. And finally, evaluate. This is huge. Is the fully normalized solution actually the best for this specific scenario? Because sometimes, in real-world applications, strict 3NF can actually lead to overly complex queries. Being able to evaluate the practicality of your own design is exactly what pushes you up into those top-grade boundaries.
When you reach that crucial evaluation stage, examiners expect you to critically analyze trade-offs using these 3 specific criteria. and they expect you to support your decisions with evidence. Let's look at space complexity first. Highly normalized databases massively reduce data redundancy. That means they take up significantly less memory and storage space. That's a huge positive, right? However, look at time complexity. If your data is split across 5 different tables to achieve 3NF, retrieving a single complete record requires incredibly complex SQL join operations. This dramatically increases execution speed time and computational overhead. You must be able to discuss this specific trade-off. Finally, edge cases. What happens if a customer registers but hasn't actually made an order yet? Does your normalized design allow for null foreign keys, or is the whole system going to crash? Analyzing these 3 factors proves you aren't just memorizing textbook rules, but you are functioning like a true high-level database administrator.
All right, moving to section 4, top examiner traps. Let's look at the common mistakes that are destroying candidate scores.
We're going to jump into a quick interactive workshop based directly on principal examiner reports. I'm giving you a 60-second mental challenge right now. Think back to your previous exam answers. Did you commit any of these top 3 fatal mistakes? Trap number 1, applying the wrong algorithm or rule for the context. For example, treating a super simple single entity scenario as if it needs some massive complex relational architecture. Trap number 2, ignoring boundary conditions or edge cases exactly like we just discussed. Failing to account for extreme or unusual data inputs that would completely break your rigid database constraints. But listen closely. The most dangerous, the absolute classic trap is number 3, providing generic, non-specific answers. This is the Alex trap we talked about earlier. Examiners will literally give you 0 marks for a perfect textbook definition if it is not explicitly tied to the nouns and verbs used in that specific exam prompt. 0.
Let's do a 30-second speed writing comparison to show you exactly how to transform a generic mark-losing sentence into a context-specific, peel-structured masterclass. Look at the flawed example first. Normalization reduces data redundancy. Okay, it's technically true, but it's totally generic. An examiner reads that and thinks, okay, you've read a textbook, but you haven't read my exam question. Now, look at the perfect example. Applying 3NF to the customer table reduces update anomalies when a customer changes their phone number. Wow, look at the difference. It identifies the specific level of normalization, 3NF. It names the specific entity from the scenario, the customer table, and it gives a concrete contextual result, reducing update anomalies for phone numbers. That right there is how you guarantee maximum marks.
To help you avoid these examiner traps when you're under the intense, ticking clock pressure of the exam room, I want you to remember this simple acronym. It will keep your analytical framework completely locked in. CEG. It stands for context, edge cases, and given scenario. Before you put your pen down and finalize your answer, mentally check it against CEG. Does your answer address the specific context of the question? Have you considered any unusual edge cases in the data? And is every single point you are making explicitly linked back to the given scenario? If you can confidently answer yes to all 3 of those questions, your database design is bulletproof.
Integrating everything we've learned today, these 3 rules form the ultimate blueprint. This is what guarantees top marks in your Cambridge computer science papers. Rule 1, command word decoding. Never, ever just start writing. Stop. Identify if the question asks you to state, describe, explain, or evaluate. Your depth has to match that command word perfectly. Rule 2, peel application. Structure your analytical answers with point, evidence, explanation, and link to ensure maximum contextual depth every single time. Rule 3, time management matrix. Allocate your time strictly based on the marks available. Don't spend 15 minutes perfectly drawing out a 2-mark 1NF table, leaving yourself rushing through an 8-mark 3NF evaluation. That's a disaster. Stick to the system, and you will thrive. The results of utilizing this system are not just theoretical, guys. They are proven. Students who implement these exact strategies, focusing on securing method marks, using peel structures, and providing contextual evaluation, see an average improvement of 2 full grade boundaries. Let me repeat that. 2 full grade boundaries. That is the difference between a C and an A, or an A and an A star. But remember, this transformation only happens provided you practice consistently. Knowledge is potential, but practice is power. You have to take these frameworks and apply them to actual past papers over and over again until it becomes absolute second nature.
Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGC to excel in your Cambridge examinations. Subscribe right now to @aceexams_IGC and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. And before you go, think about this. As the world moves towards massive, unstructured, NoSQL databases for AI and big data, why do relational, normalized databases still form the unshakable backbone of global finance and logistics? Master the logic here, and you master the future of data. Ace the exams. Your Cambridge success starts here.